Have you ever looked up at that faint red point in the night sky and wondered, well, not just what it is, but how long it would really take to get there? You see, for generations, Mars has lived in our imagination as something almost within reach, a neighbor, a destination, a promise. Yet when we ask the simplest question, how long would it take us to go there, the answers scatter in every direction. Some say months, others say years. And that's the thing, it feels like a single journey, a straight line across empty space. But space is never empty, and it is never simple. Perhaps you imagine a rocket leaving Earth, engines roaring, heading straight toward Mars like a ship crossing an ocean. But the universe doesn't work that way. Gravity bends paths, time stretches distances, breathe in and out as planets move like dancers around the sun. Earth and Mars are never standing still, they are circling, drifting, sometimes close, sometimes impossibly far apart. And so the question of time becomes something deeper than speed, because this journey is not just about machines, it is about physics and geometry and, quietly, about the human body and mind. What does months in weightlessness do to muscle and bone? What does isolation do to thought and memory? What does radiation, invisible and relentless, do as time passes? And what happens if we rush? What do we gain and what do we risk? So when we ask how long it takes to reach Mars, we are really asking something else. I suppose we are asking how patient the universe demands us to be, and whether we are ready to listen. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. When we talk about the distance between Earth and Mars, we often speak as if it were a number you could write down once and carry with you forever, like the distance between two cities on a map. London to Paris, New York to Los Angeles. Fixed, reassuring. But space does not offer us that comfort. Space is alive with motion. Nothing waits for us. Nothing holds still. And that, perhaps, is the first quiet truth we must sit with before we even begin to talk about traveling to Mars. If you step outside on a clear night and look up, Mars appears calm, steady, almost patient, a small red ember pinned to the dark. But that stillness is an illusion born of distance. In reality, Mars is racing through space at tens of thousands of kilometers per hour, locked in an endless fall around the sun. And Earth, beneath your feet right now, is doing exactly the same thing. Two travelers on different lanes of a vast cosmic track, each moving to its own rhythm, never stopping, never slowing, never aligning just for our convenience. And that's the thing. The distance between Earth and Mars is not a single distance. It is a constantly changing relationship. Sometimes they are relatively close, neighbors passing each other on the road. Other times they are on opposite sides of the sun, separated by an almost unimaginable gulf. At their closest, they can be around 55 million kilometers apart. At their farthest, that distance can swell to more than 400 million kilometers. A difference so vast that it changes everything. Fuel, time, risk, even the very possibility of the journey. So when someone asks how far away Mars is, the honest answer is, well, it depends. It depends on where both planets are in their orbits at that moment. And those orbits are not neat circles drawn with a compass. They are stretched, slightly squashed paths, gentle ovals shaped by gravity and time. Earth moves on one of these paths, taking a little over a year to complete a full loop. Mars moves on a wider, slower one, taking almost twice as long. And because of this difference, the distance between them is always changing, like two runners on a track where one lane is longer than the other. You see, sometimes Earth catches up to Mars. Sometimes Mars pulls ahead. There are moments when Earth overtakes Mars on the inside lane, passing relatively close. These moments are rare and precious. They are called oppositions, and they are the times when Mars appears brightest in our sky. And it is during these windows that Mars is, in a very real sense, as close as it is ever going to get to us. Miss that moment and Mars begins to drift away again, day by day, month by month, pulling the finish line farther into the distance. This is why there is no single number that can answer the question of distance. Any number you hear is a snapshot frozen in time, a photograph of a relationship that is always moving. And space travel, unlike travel on Earth, cannot ignore that motion. You cannot simply aim at where Mars is now. By the time you arrive, Mars will have moved. You must aim at where it will be, and that means understanding the dance. Imagine throwing a ball to a friend who is running. You do not throw it at where they are. You throw it ahead of them, trusting that motion will bring them to the ball. Traveling to Mars is like that, except the field is millions of kilometers wide, the runners are planets, and the throw takes months. And if you misjudge, even slightly, you miss entirely. And perhaps this is where our everyday intuition begins to fail us. On Earth, distance feels static. Roads do not shift beneath us. Cities do not drift apart while we sleep. But in space, distance is a living quantity. It breathes. It stretches and contracts with the slow heartbeat of orbital mechanics. And every mission to Mars must begin by asking not how far is Mars, but how far will Mars be when we get there. This changing distance also explains why travel times vary so widely in popular discussion. One person speaks of a journey lasting 6 months. Another talks about a year, or even longer. They are not necessarily disagreeing. They may simply be imagining different starting points in the cosmic dance. Leave when Mars is near, and the path can be shorter, more efficient. Leave at the wrong time, and the journey becomes longer, more demanding, sometimes impractical. And yet, even at its closest, Mars is still astonishingly far away. 55 million kilometers is not a small number. It is more than 100 times the distance between Earth and the Moon. Light itself, the fastest thing we know, takes several minutes to cross it. Radio signals, carrying voices and data, travel at that same speed, meaning that even in the best case, conversation between Earth and Mars will always be delayed, fragmented by silence. A question asked now, an answer arriving later. A reminder that distance in space is not just physical, but temporal. As Mars moves farther away, that delay grows. At maximum separation, it can take more than 20 minutes for a signal to travel one way. A simple exchange becomes an hour-long conversation, and this is just communication. Physical travel stretches the imagination even more. The farther Mars is, the longer a spacecraft must travel, or the more energy it must spend to shorten the time. There is no escaping this trade-off. Distance demands patience, or power, or both. And power is not something we have in limitless supply. Rockets carry fuel, and fuel has mass. More fuel means more weight. More weight means more fuel to lift it. A feedback loop that quickly becomes unforgiving. This is why distance matters so deeply. Every additional kilometer must be paid for in energy. And when distance grows by hundreds of millions of kilometers, the bill becomes astronomical in the most literal sense. So engineers and scientists do not ask how to travel the straight-line distance between Earth and Mars. In space, straight lines are a luxury we cannot afford. Instead, they look for paths that follow the natural curves of gravity, using the motion of planets to their advantage. Paths that are longer in distance, perhaps, but cheaper in energy. Paths that accept the dance rather than fight it. And this brings us back to the changing distance once again. Because the most efficient paths only exist at certain times. They are not always open. Space has schedules, windows, opportunities that appear, linger briefly, and then close for years. Miss them, and you wait, not because we lack courage or ambition, but because the geometry of the solar system simply does not allow it. There is something deeply humbling about this. For all our technology, for all our talk of conquest and expansion, we remain subject to the slow, elegant mechanics of celestial motion. Earth does not hurry for us. Mars does not pause. They move as they have for billions of years, indifferent to our plans. And if we wish to travel between them, we must learn to move in harmony. So when we speak of the distance to Mars, we are really speaking of timing, of alignment, of patience. The distance is not just measured in kilometers, but in opportunities that come and go. And once we accept that, once we stop asking for a single number and begin to think in terms of motion and rhythm, a new question naturally emerges. If the distance is always changing, and if energy is precious, then how do we choose a path that respects both, and what is the quiet, elegant route that lets us reach Mars using the least possible effort, even if it asks us to take our time? And so the question quietly shifts. If the distance is alive, if it stretches and contracts with the slow turning of the planets, then the next thing we must ask is not how fast can we go, but how wisely can we move. Because in space, speed is expensive, energy is precious. And the most elegant journeys are not the ones that rush, but the ones that listen. This is where the idea of a particular path begins to emerge, almost like a whispered suggestion from the universe itself. Not a straight line, not a reckless dash across the void, but a gentle arc that borrows its shape from gravity. You see, when we leave Earth, we are already moving. Earth is carrying us around the sun at an extraordinary speed, and when a spacecraft lifts off, it inherits that motion. We do not start from rest. We are already part of the solar system's flow. And the most efficient journeys are the ones that make use of that inherited momentum rather than fighting against it. Imagine, if you will, stepping onto a moving walkway at an airport. You could try to sprint across the floor beside it, burning energy, tiring quickly. Or you could step onto the walkway and let it carry you forward, adding just a little effort of your own. Spaceflight, at its most efficient, works in much the same way. The planets themselves provide moving walkways through the solar system, and the challenge is to step on at exactly the right moment. There is a particular kind of path that does this beautifully. It is a transfer that gently lifts a spacecraft from Earth's orbit and places it onto a new orbit around the Sun, one that stretches outward until it meets Mars at just the right place and time. No sudden turns, no constant thrust, just a single push to leave Earth, a long, silent coast through space, and another gentle adjustment upon arrival. It is not the shortest path in distance, but it is the cheapest in energy. And that trade, distance for efficiency, lies at the heart of almost every mission we have ever sent to Mars. This path works because gravity is not just a force that pulls things down. It is also a sculptor of motion. By shaping orbits, gravity allows us to exchange energy with planets, to climb outward from the sun's warmth to the colder reaches where Mars travels. And by choosing an orbit that touches Earth at one end and Mars at the other, we allow the universe to do most of the work for us. But there is a cost, and that cost is time. When a spacecraft follows this gentle arc, it does not race directly toward Mars. It slowly drifts away from Earth, climbing higher and higher from the sun, its speed gradually changing as gravity reshapes its path. For months, it travels through silence, engines mostly quiet, sunlight growing fainter, Earth shrinking to a pale dot behind it. This is not a journey of constant acceleration. It is a patient fall around the sun, carefully timed so that Mars arrives at the meeting point at the exact same moment. And that's the thing. Timing is everything. Leave too early and Mars is not there when you arrive. Leave too late, and it has already passed. The window for this journey opens only when the geometry is just right, when Earth and Mars are positioned so that this shared arc exists between them. Miss it, and you must wait, not days or weeks, but years, until the slow clockwork of the solar system brings the planets back into alignment. This is why this particular route has become so popular. It asks for patience, but it offers reliability. It minimizes fuel, which means lighter spacecraft, lower costs, fewer risks during launch. It turns a violent explosion of chemical energy at liftoff into a quiet, almost meditative drift through interplanetary space. And for machines, that trade makes perfect sense. But as we begin to think about people rather than probes, the story becomes more complicated. Because time, which is so generously offered to machines, is not so easily given to humans. Months in space are not empty. They are filled with radiation, isolation, the slow erosion of muscle and bone. Every extra day matters. Every additional week adds risk, and so the very path that is kindest to our rockets is, in some ways, unkind to our bodies. Still, with the technology we have today, this path remains our best option. Chemical rockets are powerful, but they burn quickly. Once their fuel is gone, they become passengers, coasting along paths set by gravity. To shorten the journey significantly, we would need to carry vastly more fuel or develop engines that can push gently but continuously for months. And those technologies, while imagined, remain largely out of reach. So we accept the trade, we accept a longer journey in exchange for feasibility. We choose to move with the solar system rather than against it, and in doing so, we acknowledge a deeper truth. Spaceflight is not about brute force. It is about harmony, about placing ourselves within the existing rhythms of the cosmos and allowing them to carry us forward. You know, there is something almost philosophical about this. We often think of progress as speed, faster computers, faster planes, faster lives. But the journey to Mars reminds us that sometimes the most advanced path is also the slowest one. The one that respects limits. The one that listens. And yet, even within this elegant solution, variation exists. Not every journey along this path is identical. Small differences in launch energy, spacecraft mass, and mission design can stretch or compress the travel time. Some missions arrive sooner, others later. And when we look back at the long list of spacecraft that have made this crossing, a pattern begins to emerge. A cluster of times. A range that tells us something practical, something grounded in reality. If we want to understand how long it truly takes to reach Mars, not in theory, but in practice, then perhaps the most honest place to look is not at equations or idealized paths, but at the journeys that have already been made, quietly tracing these arcs across the void, one after another, teaching us, mission by mission, what this elegant route really costs in time. And so we arrive at the quiet evidence left behind by those who have already gone. Not people, not yet, but machines. Silent travelers built by human hands, flung outward from Earth with hope and calculation, each one tracing its own version of that gentle arc through space. If we want to know how long the journey to Mars really takes, not in theory, not in promise, but in reality, then these missions are our witnesses. When you line them up across the decades, something interesting begins to appear. Despite differences in design, purpose, and era, most of these spacecraft took a remarkably similar amount of time to reach Mars. Not weeks, not years, but somewhere in between, roughly 6 to 9 months, again and again, as if the solar system itself were quietly insisting on a rhythm that cannot easily be broken. This is not coincidence. It is the natural consequence of the path we choose and the limits we accept. These spacecraft were not racing. They were not crawling either. They were doing what physics allows most comfortably, coasting along that efficient arc, guided by gravity and patience. And in doing so, they revealed a truth that is sometimes uncomfortable for our expectations. With current technology, this is the tempo of interplanetary travel. Some missions arrived a little faster. Others took their time. But none of them shattered the months-long barrier by a dramatic margin. Even when engineers pushed harder, even when launch conditions were favorable, the gains were modest. Weeks shaved here, a month there. Nothing like the leap from months to days that popular imagination sometimes hopes for. And that's the thing. We often assume that all spacecraft travel at the same speed, like cars on a highway. But space does not work that way. Each mission begins with a different push from Earth, a slightly different mass, a slightly different amount of energy. And those small differences, accumulated over millions of kilometers, can lead to noticeable changes in arrival time. A lighter spacecraft can be accelerated a bit more easily. A launch that happens right at the optimal moment can take advantage of planetary alignment. A mission designed only to fly by Mars does not need to slow down as much as one that must enter orbit or land. And all of these factors quietly shape the clock. So when we look at the record, we see variation, but we also see constraint. The variation lies within a narrow band, a corridor carved out by physics. You can move within it, but you cannot escape it without changing the rules entirely. It is also worth noticing that these spacecraft were not always aiming for the same destination. Some were headed for orbit, some for the surface, some merely passing by, stealing a glimpse before continuing onward. Each goal demands its own approach, its own timing, its own sacrifices. Slowing down to be captured by Mars takes energy that must be budgeted long before launch. And sometimes that means accepting a slightly longer journey in exchange for a safer arrival. And safety matters even for machines. A rush trajectory can mean higher speeds at arrival, which increases the risk of failure. Miss the timing by a little, misjudge the burn, and a spacecraft can skip off into space or burn up in the atmosphere. So engineers tend to favor reliability over haste. Mars will still be there in a few months. A lost spacecraft will not be replaced so easily. When you step back and let these stories overlap, a pattern emerges that feels almost like a conversation across time. Mission after mission quietly agreeing with the last. This is how long it takes. This is the cost of doing it right. And perhaps most importantly, this is what our current technology can realistically achieve. But even within this pattern, there are subtle lessons. Some missions took longer not because they were slower, but because they left at less than ideal times. The alignment was not perfect. The launch window was narrow, and rather than wait years, engineers chose a path that worked, even if it meant adding weeks or months to the journey. That choice reveals something deeply human. We are willing to accept time as a price for opportunity. And then there are the missions that pushed closer to the lower end of that range. They left at just the right moment. They carried just enough energy. They rode the gravitational currents with remarkable precision. These are often held up as examples of what is possible. But even they did not escape the fundamental limit. They did not arrive in 3 months. They did not arrive in 1. They arrived when the universe allowed them to. This brings us to a quiet but important realization. The 6 to 9 month journey is not a technological failure. It is not the result of inefficiency or lack of imagination. It is the natural outcome of balancing energy, safety, and alignment within the solar system we actually inhabit. To do dramatically better, we would need to change one of those ingredients in a profound way. And this is where the question begins to shift again. Because if machines already show us what is typical, what is repeatable, then we must ask why we cannot simply choose to go faster. After all, rockets can achieve incredible speeds. We have sent probes hurtling out of the solar system entirely, so why not point that power at Mars and arrive sooner? The answer, as always in space, is layered. Speed is not free. Gaining it costs fuel. Carrying fuel costs mass, and mass makes everything harder. Every additional kilometer per second demands an exponential increase in energy. And at some point, the rocket equation becomes less of an equation and more of a wall. Those past missions illustrate this beautifully, though quietly. They show us that the problem is not reaching Mars. We have done that many times. The problem is reaching Mars efficiently, predictably, and safely. And when those constraints are honored, the timeline settles into that familiar range. And there is something oddly comforting about that. The universe, vast and indifferent though it may be, offers us a narrow path that works. It does not promise speed. It promises consistency. And consistency is what allows planning, preparation, and eventually, perhaps, human presence. But as soon as we begin to imagine people instead of probes, the discomfort returns. 6 to 9 months is a long time to be suspended between worlds. It is long enough for bodies to weaken, for minds to wander, for radiation to quietly accumulate. And so the very number that history gives us as typical also becomes a challenge, a limit we may one day wish to push against. To push against it, however, we must confront a simple but stubborn truth. Wanting to go faster does not make it so. The solar system does not reward impatience. It demands payment in energy. And the next question, the one that naturally follows from all these journeys already made, is not how long have past missions taken, but what exactly prevents us from simply accelerating harder and arriving sooner, and why speed in space is never as straightforward as it sounds. And so we come to the idea that feels at first almost irresistible. If the journey takes months, if time itself is the burden, then why not simply go faster? After all, speed is something we understand intuitively. On Earth, if a trip takes too long, we press the accelerator. We build faster trains, stronger engines, more direct routes. It feels natural to ask the same of space. Why not point the rocket straight at Mars, light the engines, and keep pushing until we arrive? But space, you see, is not a road. It has no asphalt, no friction to lean against, no simple way to trade fuel for speed without consequence. Every increase in velocity comes with a price that grows faster than our intuition expects. And that price is written in energy. When a spacecraft leaves Earth, it must first overcome gravity just to escape the planet's hold. That alone requires an enormous burst of power. But once free, the challenge does not end. The spacecraft is still bound to the sun, still moving within its gravitational field. To go faster toward Mars is not simply to accelerate forward. It is to climb out of one gravitational well and reshape an entire orbit around the sun. And that reshaping is expensive. We often imagine space as empty, but it is anything but. It is structured by invisible contours of gravity, like valleys and hills carved into space-time itself. Planets sit at the bottom of these valleys. To move between them, you must climb out, cross a ridge, and descend again. And the steeper you want that climb to be, the more energy you must carry with you from the very beginning. This is where the limits of our rockets quietly assert themselves. Chemical rockets, the kind we rely on today, deliver tremendous thrust, but only for a short time. They burn fuel violently, expelling it at high speed to push the spacecraft forward. Once that fuel is gone, the engine falls silent. There is no coasting thrust, no gradual acceleration. just motion set at launch, slowly sculpted by gravity. So if you want to arrive at Mars faster, you must begin the journey with more speed. And to do that, you must bring more fuel. But more fuel means more mass. And more mass means you need even more fuel to lift it off Earth in the first place. This feedback loop is unforgiving. Each attempt to push harder makes the rocket heavier, which makes pushing harder still more difficult. It is a spiral that engineers know intimately and respect deeply. This relationship between mass and velocity is not linear. It is exponential. That means doubling your speed does not require double the energy. It requires far more. At some point, the numbers stop being practical. The rocket grows absurdly large. The cost becomes staggering, and the risks multiply. And risk is not just about explosions on the launch pad. Higher speeds mean higher energies throughout the journey. Arriving at Mars too fast creates its own problems. You must slow down to enter orbit or land. That slowing down also costs energy. Miss the window, miscalculate the burn, and the spacecraft may fly past Mars entirely, lost to interplanetary space, or slam into the atmosphere with catastrophic force. This is why going faster is not simply a matter of desire. It is a matter of balance. Engineers must choose a speed that allows for controlled arrival, one that leaves room for correction, one that respects the limits of navigation, communication, and hardware reliability. And space does not forgive mistakes easily. There is no roadside assistance between planets. A small error early in the journey can grow silently over millions of kilometers, becoming impossible to fix when it finally reveals itself. Faster travel compresses the timeline for correction, shrinking the margin for error until it becomes uncomfortably thin. There is also the matter of direction. Spacecraft do not travel in straight lines relative to the Sun. They follow curved paths shaped by orbital mechanics. To fly straight at Mars would mean constantly correcting your trajectory, continuously firing engines to counteract gravity. That requires sustained thrust, not brief bursts, and sustained thrust demands engines capable of operating for months, not minutes. Such engines exist in concept and even in limited practice, but they produce very small forces. Ion engines, for example, can run for years, gently pushing a spacecraft to high speeds over time. But their thrust is so low that they cannot lift off Earth. They must be paired with traditional rockets, adding complexity and mass. And even then, their acceleration is slow, measured in fractions of the force you feel when you rest your hand on a table. So we find ourselves in a curious position. We can go fast briefly, or we can go slowly for a long time. But combining high speed and long duration remains one of the great challenges of spaceflight. And until that challenge is solved, our journeys remain bounded by the physics we already understand. This is why space is not a highway. On a highway, you can choose your speed independently of the road itself. In space, your speed is inseparable from the gravitational landscape. Every attempt to rush must wrestle with forces that have been shaping the solar system for billions of years. And those forces do not yield easily. Perhaps there is something humbling in this realization. We like to think of ourselves as masters of technology, capable of bending nature to our will. But the journey to Mars reminds us that mastery often means restraint, knowing when not to push, knowing when to let the universe lead. And yet, the desire to go faster does not fade, especially when we begin to think about human travelers. Months in space are not merely inconvenient, they are dangerous. Radiation exposure increases with time, muscles weaken, bones lose density, minds strain under isolation and confinement. Every extra day adds weight to the mission in ways that do not show up in equations alone. So the pressure builds. Faster is safer, in some respects. Shorter journeys mean less exposure, less risk, and this creates a tension at the heart of Mars exploration. Physics asks us to be patient. Biology urges us to hurry. And that tension leads us naturally to the next constraint, one that quietly governs everything we have discussed so far. Even if we accept slower paths and efficient arcs, even if we resist the urge to push harder than physics allows, we still cannot leave whenever we wish. The solar system itself sets the schedule. There are moments when the path opens, and long stretches when it does not. And understanding those moments, those precious windows of opportunity, becomes the next essential piece of the journey. And so the universe tightens the rules once again. Even if we accept the limits of speed, even if we make peace with patience and efficiency, there remains one final constraint that cannot be negotiated. We cannot leave whenever we wish. Space, you see, runs on a timetable that has nothing to do with our calendars, our politics, or our sense of urgency. It moves to a rhythm set by orbital mechanics, by gravity, by the slow turning of worlds around the sun. There are moments when Earth and Mars align in just the right way, when that gentle arc through space opens like a door. And then there are long stretches when that door is firmly closed. These moments are rare, predictable, and unforgiving. Miss them, and the journey becomes longer, harder, sometimes impossible with the technology we have. Imagine standing on the shore of a vast ocean, watching the tide. You cannot decide when it comes in. You cannot command it to wait for you. You can only observe, calculate, and be ready. Launching toward Mars is much the same. The planets must be positioned so that a spacecraft leaving Earth can naturally fall into the right solar orbit, one that intersects Mars at the proper time. Without that alignment, no amount of desire or engineering bravado will create an efficient path. Earth moves faster around the sun than Mars. Every day it gains a little ground. Slowly, patiently, it catches up. When Earth finally overtakes Mars, passing it on the inside lane, the distance between them shrinks. This is the moment of opportunity. A narrow window when the energy required to travel between the two worlds reaches a minimum. And during this window, missions are planned, rockets prepared, countdowns whispered. But this window does not stay open long. A few weeks, perhaps a couple of months at most, before the geometry begins to fall apart again. Earth pulls ahead. Mars lags behind. The distance grows. The arc that once fit so neatly between them stretches, twists, and eventually breaks. The door closes. And then we wait. The waiting is not arbitrary. It is written into the clockwork of the solar system. Earth must lap Mars once more, completing another cycle before the geometry returns. This takes a little over 2 Earth years. 2 years of planning. 2 years of refinement. 2 years of watching and calculating, knowing that the universe will offer another chance, but only on its own terms. And that's the thing. Space travel does not reward spontaneity. It demands foresight. Every Mars mission is planned years in advance, anchored to a launch date that cannot slip easily. Miss it by days, and the cost rises. Miss it by weeks, and the mission may be lost entirely. Rockets do not simply wait on the pad for better alignment. Fuel degrades. Budgets expire. Political will shifts. The window closes, and with it, years of work. If we choose to ignore this schedule and launch at a poor time, the consequences are severe. The spacecraft must travel a longer path, burning more fuel, taking more time. In some cases, the journey can stretch from months into years. And for human missions, such delays are unacceptable. Every additional day in deep space compounds risk, from radiation to psychological strain. So the launch window becomes more than a technical detail. It becomes a gatekeeper. It decides when Mars is accessible and when it is not. It shapes the cadence of exploration itself. Entire generations of engineers and scientists organize their careers around these moments. Miss one window, and you may not see the next. And there is something almost poetic about that. For all our talk of conquering space, we remain bound to cycles older than humanity itself. The orbits of Earth and Mars have been repeating this dance for billions of years, long before rockets, long before life, and they will continue long after we are gone. Our missions are brief interruptions, timed to slip between those steps. This constraint also explains why Mars exploration comes in waves, bursts of activity followed by long lulls, a cluster of launches, then silence. It is not indecision, it is geometry, the solar system opening and closing its doors, and this rhythm forces compromise. If a mission is not ready when the window opens, it cannot simply launch late and hope for the best. Engineers must decide whether to delay by years or accept a less efficient trajectory. Each choice carries cost, more fuel, more complexity, more risk, and these trade-offs become sharper as missions grow more ambitious. For robotic explorers, the universe can be patient. Machines do not mind waiting longer. They do not fear isolation. They do not weaken in microgravity. But for humans, the calculus changes. A launch window missed is not just a delay. It is a profound shift in mission design. Supplies must last longer. Radiation exposure increases. Psychological pressures intensify. The margin for error shrinks, and so, the question of when becomes as important as how. We do not ask merely how long the journey takes, but when it can begin at all. And this leads us naturally to a deeper tension. If the universe only gives us narrow windows, and if those windows force us into long journeys, Then what happens if we try to shorten the travel time itself? What happens when we attempt to bend these rules, to trade fuel and complexity for speed, to arrive sooner even if the window is not perfect? Because the moment we begin to ask whether we can go faster, truly faster, we step into a realm where the costs rise sharply and the risks multiply, where bold ideas promise shorter voyages but demand sacrifices that are anything but small. And so the temptation grows stronger. If waiting for the perfect window already asks so much patience of us, then surely there must be a way to reclaim some of that time in transit. Surely, we think, if we can accept greater cost, greater complexity, greater daring, we can shorten the journey itself. And on paper, you see, this is true. There are trajectories that cut the travel time dramatically, 3 months, 4, perhaps. Numbers that sound almost reasonable when compared to the long, silent half-year drift we have grown accustomed to. But the universe is very careful about how it grants such favors. To shorten the journey to Mars, you must arrive there sooner than gravity alone would allow. And that means carrying far more energy at the very beginning. Instead of gently falling outward from Earth's orbit, you must leap. You must push hard, early, and relentlessly. The spacecraft leaves Earth not as a patient participant in the solar system's flow, but as something trying to muscle its way through it. That initial push is everything. To cut months from the journey, the spacecraft must depart Earth with a much higher speed relative to the Sun, and achieving that speed with chemical rockets is brutally expensive. The fuel required does not increase politely. It grows at a rate that feels almost punitive. Each additional reduction in travel time demands disproportionately more propellant, more mass, more structural strength, more everything. Rockets are strange machines. Most of what they launch is fuel used to lift fuel used to lift fuel. The payload, the thing you actually care about, is a small fraction at the top. When you try to go faster, that fraction shrinks further. At some point, you are building a rocket almost entirely to support its own ambition. And that ambition does not stop at launch. Higher departure speeds mean higher stresses throughout the spacecraft. Structures must withstand greater forces. Tanks must hold more propellant. Engines must burn hotter longer, closer to their limits. The margin for error narrows. The graceful simplicity of a coasting journey gives way to a mission profile filled with aggressive burns and tight tolerances. Then there is the matter of arrival. If you rush toward Mars, you do not magically slow down when you get there. You arrive screaming fast, carrying all that extra kinetic energy with you. And Mars, unlike Earth, has a thin atmosphere and weaker gravity. It is not forgiving. Slowing down enough to enter orbit or land safely becomes a major challenge. You must carry additional fuel just to brake, or rely on atmospheric drag that may not be sufficient. Either way, the problem compounds. And this is where the numbers begin to spiral. More fuel to go faster, more fuel to slow down, more mass to support both, more structure to hold it together, and every kilogram added at the top demands many more at the bottom. Engineers call this tyranny, and it is not hyperbole. It is a fundamental constraint. On top of this, faster trajectories are less flexible. When you travel slowly, you have time. Time to correct small errors. Time to adjust course. Time to respond to unexpected problems. When you rush, you compress the entire mission timeline. Decisions must be made quickly. Corrections must be precise. A minor navigation error can grow rapidly, leaving little opportunity for recovery. And space is unforgiving of haste. A miscalculation that might be survivable on a slower path can be catastrophic on a faster one. There is simply less room to breathe. The costs, too, rise sharply. Not just financial, though those are enormous, but logistical and political as well. Bigger rockets, more complex missions, higher stakes. Every launch becomes a high-wire act with little tolerance for failure. And when humans are involved, that risk takes on a different weight. Because while shorter travel times reduce exposure to radiation and microgravity, they increase exposure to launch and arrival hazards, violent accelerations, intense vibrations, narrow safety margins. The body can tolerate a lot, but not without consequence. The question becomes not just can we go faster, but should we? And yet these ideas are not fantasies. They are studied seriously. Engineers model them. Agencies debate them. The math works, in principle. With enough fuel and enough power, you can cut the journey to Mars significantly. The universe does not forbid it. It simply sends the bill. And that bill is not one we have been willing to pay, at least not yet. Instead, we compromise. We accept longer journeys in exchange for reliability. We choose trajectories that have been flown before, paths that we understand, because Mars is already hard enough without adding unnecessary risk. Still, the dream of speed persists, especially when we consider the human cost of time. Every extra month spent in deep space is another month of muscle loss, bone thinning, psychological strain. Time itself becomes a threat, and so the balance shifts again. Faster may be more dangerous in some ways, but slower is dangerous too. This is the quiet paradox at the heart of human spaceflight. The safest path for machines is not necessarily the safest path for people. The universe offers us efficiency or speed, but rarely both, and choosing between them forces us to confront the limits of our technology and the fragility of our bodies at the same time. As we push these faster concepts further, another truth becomes clear. Even if we solve the engineering challenges, even if we accept the cost and risk, speed alone does not protect us from everything. There are dangers in space that do not care how fast you are moving. Invisible dangers that accumulate silently, day after day, indifferent to our ambitions. And that realization pulls us gently toward the next concern. Because no matter how elegant the trajectory, no matter how short the journey, humans are not cargo. They are living systems, shaped by gravity, shielded by atmosphere, adapted to Earth in ways that space slowly, relentlessly begins to undo. And understanding what time and space does to the human body becomes just as important as understanding how to shorten that time at all. And so, quietly, almost reluctantly, we turn our attention away from engines and trajectories and begin to look inward. Because at some point, Mars stops being a problem of machines and becomes a problem of people. And that's the thing we so often forget. Humans are not containers to be shipped. They are not inert payloads. They are living systems shaped by millions of years of evolution under very specific conditions. Gravity, atmosphere, day and night. Earth has tuned us with exquisite precision, and space does not care about any of that. The moment a human leaves Earth, something fundamental changes. Gravity, which has been a constant companion since before birth, fades away. At first, this feels liberating. Astronauts float, objects drift, movement becomes effortless. But beneath that beauty, the body begins to adapt in ways that are anything but helpful for long journeys. Muscles, you see, exist for a reason. They push against gravity. They hold us upright. Take gravity away, and the body begins to ask a simple question. Why keep all this muscle if it is no longer needed? And so it doesn't. Muscle mass begins to decline. Strength fades. Even with hours of daily exercise, astronauts lose significant muscle over time. And the longer the journey, the harder it is to fight that loss. Bones tell a similar story. On Earth, they are constantly stressed by our weight. That stress signals the body to maintain bone density. Remove it, and the signal disappears. Calcium leaches out. Bones become weaker, more brittle. In just a few months, astronauts can lose bone density equivalent to years of aging on Earth. And unlike muscle, bone does not recover easily. Some losses may never fully reverse. And this is not just an inconvenience. For a mission to Mars, it becomes a serious risk. We are not talking about floating in a space station and then returning home to gravity and hospitals. We are talking about landing on another planet, a planet with gravity, a planet where astronauts must walk, lift, work, and survive. Arriving after months in microgravity, with weakened bones and muscles, is not a trivial concern. It is a potential mission-ending one. Then there is the cardiovascular system. On Earth, gravity pulls blood downward. The heart works constantly to pump it upward. In space, that struggle vanishes. Blood redistributes toward the head. Faces puff up, legs thin. The heart itself begins to weaken, no longer needing to work as hard. And when gravity returns, whether on Mars or back on Earth, the system can struggle to cope. Dizziness, fainting, loss of coordination, all of these become more likely the longer the body has forgotten what gravity feels like. But physical changes are only part of the story. The mind, perhaps, is even more sensitive to time and space. Humans are social creatures. We evolved in groups, surrounded by familiar faces, familiar sounds, familiar landscapes. A journey to Mars strips almost all of that away. The crew is small. The environment is artificial. The view rarely changes. Day after day, month after month, the same walls, the same routines, the same voices. Isolation begins quietly. At first, there is excitement, purpose, a sense of history unfolding. But over time, novelty fades. Small irritations grow. misunderstandings linger longer than they should. There is no escape, no private space in the way we understand it on Earth. Even silence becomes crowded, and then there is distance. Not just physical distance, but temporal distance. Communication delays stretch conversations into something strange and fragmented. A question sent to Earth waits in silence. An answer arrives long after the moment has passed. Real-time support disappears. The crew becomes truly alone, responsible for decisions that may carry life or death consequences without immediate guidance. Psychologists have studied this in analog environments on Earth. Remote research stations, submarines, simulated missions in deserts and Arctic ice. Again and again the same patterns emerge. Stress accumulates, sleep cycles drift, motivation fluctuates. The mind begins to turn inward, sometimes unhelpfully so. And the longer the mission, the greater these effects become. A few weeks is manageable. A few months is challenging. A year or more begins to push the limits of what we understand about human endurance. And a Mars mission, even under ideal conditions, stretches far beyond what we have ever attempted with humans before. This is why time is not just a number on a mission plan. It is a biological variable. Every additional day in space carries cost, not just in supplies and fuel, but in human resilience. The body degrades, the mind strains, and these effects do not scale linearly. They interact. Physical weakness can affect morale. Psychological stress can reduce motivation to exercise. Fatigue can lead to mistakes, and in space, mistakes compound quickly. Perhaps most unsettling of all is that we do not yet know the full extent of these risks. We have never sent humans beyond the protective bubble of Earth's magnetic field for months at a time. Low Earth orbit still offers some shielding. Mars does not. The space between planets is harsher, quieter, more exposed. And this uncertainty adds another layer of weight to the problem of time. Shorter journeys reduce exposure. Longer journeys magnify unknowns. And yet, as we have seen, shortening the journey demands technologies and risks of its own. So the human body becomes the battleground where all these trade-offs meet. Physics pulls one way, biology pulls another. Engineering stands between them, trying to negotiate a compromise that does not break either. And as if all this were not enough, there is one more threat that pays no attention to muscle or morale, no attention to speed or patience. A threat that moves at nearly the speed of light, invisible, relentless, and indifferent to whether a journey takes 3 months or 9. Because while the human body struggles quietly with weightlessness and isolation, space itself is bathing every traveler in a constant storm of radiation. And understanding that storm, and how time magnifies its danger, becomes the next essential piece of this story. And so we arrive at an enemy that does not announce itself. It makes no sound. It leaves no visible trace in the air. And yet it is everywhere, flowing endlessly through the space between worlds. Radiation is the quiet companion of every journey beyond Earth, and unlike distance or speed, it cannot be negotiated with patience alone. On Earth, we live sheltered lives without ever really noticing it. Our planet wraps itself around us like a cocoon. A thick atmosphere absorbs much of the incoming radiation from space, and a powerful magnetic field bends charged particles away, guiding them harmlessly around the planet. We walk beneath this invisible umbrella every day, rarely aware of how much danger it quietly deflects. But the moment a spacecraft leaves Earth, that protection begins to fade. First slowly, then completely. Beyond low Earth orbit, the magnetic shield weakens. Beyond it entirely, there is nothing. No atmosphere, no planetary field. Just open space, flooded with high-energy particles arriving from the sun and from far beyond the solar system itself. These particles travel at extraordinary speeds, some approaching the speed of light. They pass through spacecraft walls as if they were thin paper. They pass through human tissue, through cells, through DNA. Each interaction leaves a tiny scar, a small disruption. One alone is insignificant. Millions accumulated over time are not. And that's the thing. Radiation is not about moments. It is about duration. The longer you remain exposed, the greater the dose your body absorbs. Time becomes the multiplier. Every additional day in deep space adds to a total that cannot be undone. There are different kinds of radiation out there. Some comes from the sun, bursts of energetic particles released during solar storms. These events can be sudden, intense, and dangerous. Others come from deep space, remnants of ancient supernovae. Particles that have been traveling the galaxy for millions of years before crossing your path. These are rarer, but far more energetic, capable of penetrating deeply into matter. Inside the human body, these particles can damage cells directly or create cascades of secondary particles that do even more harm. DNA strands can be broken. Cellular repair mechanisms can be overwhelmed. Over time, the risk of cancer increases. The risk of neurological damage rises. The immune system may weaken. These are not immediate effects. They are slow, probabilistic, difficult to predict, and that uncertainty makes them particularly unsettling. Astronauts in low Earth orbit already receive higher radiation doses than people on the surface. Even there, inside Earth's protective field, exposure is a known concern. But the journey to Mars lies entirely outside that protection. Months in interplanetary space mean absorbing radiation at levels humanity has never experienced before. And, this is where time becomes the enemy again. A 6-month journey means 6 months of exposure. A 9-month journey means 50% more. Add time spent on the Martian surface, where the atmosphere is thin and the magnetic field weak, and the dose continues to rise. Then add the return journey. The total mission time stretches into years, and the cumulative radiation exposure begins to approach, and in some scenarios exceed limits considered acceptable for human health. This is not speculation. These limits are carefully studied. They are based on decades of research, on data from astronauts, from medical imaging, from radiation workers on Earth. They represent a balance between risk and practicality. Exceed them, and the probability of serious health consequences rises sharply. And yet, a Mars mission almost inevitably pushes against these boundaries. Even with optimistic assumptions, even with shielding, even with careful timing to avoid solar storms, radiation remains one of the most stubborn obstacles. You can reduce it, but you cannot eliminate it. You can shield against some particles, but the most energetic ones pass through almost anything we can reasonably launch. Shielding itself presents another trade-off. Dense materials block radiation more effectively, but they are heavy. Add too much shielding, and the spacecraft becomes prohibitively massive. Use lighter materials and protection drops. Engineers search for clever solutions, using water, fuel, or supplies as partial shielding, placing crew quarters behind them. Every design is a compromise, and the cruel irony is that faster missions, while reducing time exposure, often require higher energies that may increase radiation risk during launch and transit. Slower missions reduce peak stresses but extend exposure duration. Once again, there is no free choice. Every path carries its own balance of danger. Perhaps the most troubling aspect of radiation is that it does not care how prepared you feel. You cannot exercise your way out of it. You cannot meditate it away. It does not respond to morale or teamwork. It accumulates quietly, indifferent to human resilience. And yet humans are remarkably adaptable. Our cells repair damage constantly. Our bodies endure far more than we consciously realize. The challenge is not whether we can survive some radiation. It is whether we can survive enough of it, over long enough time, and still arrive at Mars capable of doing meaningful work and returning home safely. This question brings us back, once again, to time. Shorter journeys reduce exposure. Longer journeys magnify it. Every discussion of propulsion, of launch windows, of speed, ultimately feeds into this invisible ledger that radiation keeps with perfect accuracy. And this is why radiation is often described as the silent killer of space exploration, not because it strikes suddenly, but because it waits. It builds. It turns time itself into a hazard. So as we stand at this point in the story, we find ourselves facing a convergence of limits. Distance demands patience. Speed demands energy. The human body demands care. Radiation demands brevity. And all of these demands intersect in the same narrow corridor of possibility, which leads us, inevitably, to the question of technology. Where are we now, really? What tools do we actually possess, not in dreams or prototypes, but in operational reality? Because before we imagine breakthroughs and future engines, we must first be honest about what is currently carrying our spacecraft into space, and why, despite decades of effort, it still defines the pace of our journey to Mars. And so, after tracing all these limits back to their sources, after watching time stretch under the weight of biology and radiation and celestial mechanics, we arrive at a sobering place. We arrive at the present. Not the imagined future, not the glossy promise of concept art, but the tools we actually have in our hands right now. And when we look closely, when we strip away the romance, something becomes very clear. The journey to Mars is still defined by the same kind of machines that first carried us into space. At the heart of almost every mission today lies chemical propulsion. It is powerful, violent, and brief, a controlled explosion, repeated thousands of times per second, pushing hot gas backward to force the spacecraft forward. This technology is old by space standards. Its principles were understood long before the first satellite ever touched orbit. And yet, for all its age, it remains the backbone of space travel. There is a reason for this. Chemical rockets deliver enormous thrust. They can lift heavy payloads off Earth's deep gravitational well. They can accelerate spacecraft quickly, decisively, when it matters most. No other propulsion system we currently possess can do this with the same reliability. And reliability, you see, is everything. Space does not forgive uncertainty, but chemical rockets come with a limitation that shadows every Mars mission we plan. They burn their fuel quickly. Minutes, sometimes seconds of intense acceleration and then silence. After that, the spacecraft is on its own, coasting through space, shaped only by gravity and the occasional small correction burn. There is no sustained push, no gradual buildup of speed. What you leave Earth with is largely what you live with for the rest of the journey. This is why our trajectories look the way they do. Why they are gentle arcs instead of bold lines. Chemical propulsion excels at getting you off the ground, but it is not designed for long, continuous acceleration. And until that changes, our travel times remain bound to months, not weeks. There are, of course, other technologies. Ion engines whisper rather than roar. They expel charged particles at extraordinary speeds, producing a tiny but continuous thrust. Over long periods, they can achieve impressive velocities. Probes using them have traveled farther and faster than chemical propulsion alone would allow. But ion engines have their own constraints. Their thrust is incredibly small. You could rest your hand on one and barely feel it. They cannot lift off from Earth. They cannot push massive crewed spacecraft quickly. They require large amounts of electrical power, which in turn demands heavy solar panels or reactors. And while they are excellent for robotic missions, scaling them up for human travel remains a formidable challenge. Then there are nuclear concepts. Engines that use nuclear reactions to heat propellant or generate electricity. On paper, they promise higher efficiency, shorter travel times, greater flexibility. They sit tantalizingly close to what we might need to break free from the 6 to 9 month corridor. And yet, they remain largely experimental. Political concerns, safety fears, technical complexity. Launching nuclear material from Earth carries risks that society has not yet fully accepted. Testing such systems is difficult, costly, slow, and so progress crawls not because the ideas lack merit, but because reality moves cautiously around them. This gap between what we can imagine and what we can deploy is one of the most important truths in space exploration. Many concepts work beautifully on paper, some even in laboratories, but space is unforgiving of half measures. A propulsion system must work perfectly, every time, in an environment where repair is almost impossible. That standard filters out many promising ideas before they ever leave the ground. And so, for now, we return again and again to chemical rockets, pairing them with clever trajectories, careful timing, and incremental improvements. Better engines, lighter materials, more efficient designs. Each step forward is real but modest. There has been no sudden leap, no revolution that halves travel time overnight. And perhaps that is why Mars feels both close and distant at the same time. Astronomically, it is our neighbor. Technologically, it remains just beyond the comfortable reach of our current systems. Not unreachable, but demanding. There is something quietly profound about this plateau. It reminds us that progress is not always dramatic. Sometimes it is a long period of refinement, of learning the boundaries of what works before the next breakthrough becomes possible. The absence of a leap does not mean stagnation. It means preparation. Because every mission we fly teaches us something about propulsion, about life support, about human resilience, about radiation. Each one tightens the constraints, clarifies the problem, sharpens the questions we need to ask. And slowly, the shape of the solution becomes clearer. So when we ask where technology stands today, the honest answer is this: we can reach Mars. We have done it many times with machines. We can plan a human mission that works on paper, but doing so safely, reliably, and repeatedly pushes our current systems to their limits. Not past them, but right up against the edge. And standing at that edge naturally invites us to look forward. If chemical rockets define our present, what might define our future? What ideas are waiting, half-formed, in laboratories and simulations? What engines? What energy sources? What new compromises might one day reshape the journey itself? Because the next step is not about squeezing a few more percent out of what we already have. It is about changing the rules of the game, carefully, deliberately, with full awareness of the risks involved. And those ideas, those future paths, are already being imagined, even if they remain just out of reach for now. And so our gaze lifts, cautiously, toward the future. Not the kind of future painted in bold strokes and glossy renders, but one shaped by careful thinking, by engineers and physicists who understand just how unforgiving space can be. Because every time we imagine cutting the journey to Mars in half, or more, the universe asks the same quiet question in return. At what cost? Ion propulsion is often the first idea people reach for. It feels elegant, almost poetic. Instead of burning fuel violently, it sips, it whispers. Charged particles are accelerated to extraordinary speeds and gently expelled, producing a continuous push that can last for months or even years. Over time, that whisper adds up. Spacecraft using this method have already proven that slow, steady acceleration can achieve velocities chemical rockets can never reach on their own. But you see, the elegance hides a limitation. Thrust is tiny. So small that you would not notice it if you were standing next to the engine. This is perfect for robotic probes that can afford to wait, that do not need to fight Earth's gravity, that are content to accelerate gradually once already in space. But humans are impatient creatures, biologically if not emotionally, and human missions carry mass, life support systems, shielding, habitats, supplies. Ion engines struggle under that weight. To make ion propulsion viable for people, we would need vast amounts of electrical power. Solar panels large enough to span football fields, growing less effective as the spacecraft moves farther from the sun. Or nuclear reactors, compact, reliable, safe enough to operate for years without maintenance. And here again, we run into reality. Power generation becomes the bottleneck. The engine itself may be efficient, but without power it is silent. Then there is nuclear propulsion in a more direct sense, using nuclear reactions not just to generate electricity, but to heat propellant directly, expelling it at higher speeds than chemical engines ever could. On paper, this is compelling. Higher efficiency, shorter travel times, greater flexibility in mission design, the ability to speed up and slow down more freely. And yet, the obstacles are formidable. Nuclear systems are complex. They must be shielded to protect the crew, adding mass. They must be tested extensively, yet testing nuclear engines on Earth carries political and environmental concerns. Launching them raises fears, even if those fears are not always scientifically justified. Public trust becomes part of the engineering challenge. There are also concepts that border on science fiction. Ideas that stretch our understanding of physics but do not break it. Fusion propulsion, for instance, promises incredible energy density. In theory, it could enable rapid transit across the solar system. But controlled fusion remains elusive even for power plants on Earth. Shrinking such a system, making it reliable enough for space, is a challenge layered on top of another unsolved challenge. And this is the pattern that repeats itself. The more powerful the technology, the more complex the problem of safety becomes. Faster engines mean higher energies. Higher energies mean greater risks if something goes wrong. Radiation, heat, structural stress, failure modes that unfold too quickly to correct. The universe allows speed, but it demands precision in exchange. Perhaps that is why progress feels slow. Not because humanity lacks imagination, but because space punishes overconfidence. Every step forward must be earned, tested, understood. A breakthrough that works once is not enough. It must work every time, far from Earth, without rescue. And so the future of Mars travel is likely not a single dramatic leap, but a series of careful shifts. Better power systems, smarter shielding, hybrid propulsion methods that combine the strengths of different technologies. Incremental reductions in travel time rather than miraculous ones. And even then, shortening the journey does not solve everything. Arriving sooner does not remove the need to land safely, to survive on Mars, to wait for the right moment to return. Time saved in transit may simply reappear elsewhere in the mission. Which brings us to a subtle but crucial realization. The journey to Mars is not just the flight there. It is the entire arc of the mission. Departure, transit, arrival, stay, return. A single thread stretched across years. And when you look at it that way, shaving a few months off one segment begins to feel less transformative than it first appears. So, as we imagine faster engines and brighter futures, we must keep the whole story in view. Because even the most advanced propulsion system cannot change the fact that Mars does not offer immediate return. The planets will not realign on command. Astronauts may arrive quickly, but they may have to wait patiently for the universe to open the door home again. And that realization draws us gently toward the next truth. That time to Mars is only half the question. The other half is what happens after arrival. How long one must stay, how long one must wait, and how the simple act of coming back stretches the mission into something far longer and far more demanding than a single outbound journey ever suggests. And this is where the story quietly deepens. Because until now, we have spoken as if reaching Mars were the end of the journey, as if the moment a spacecraft touches the red soil, the problem is solved. But you see, arriving is only a pause, not a conclusion. Time, once again, refuses to let us off so easily. Mars is not a place you can simply visit and then turn around whenever you like. The same celestial mechanics that govern departure also govern return. The same dance of planets that opens a window to go there closes it again just as firmly. And when astronauts arrive on Mars, they do so knowing that the door back to Earth will not open for a long time. This is one of the most counterintuitive truths about interplanetary travel. You might imagine a quick trip there, a brief stay, and then a return home. But the universe does not arrange itself that way. Once on Mars, crews may need to wait many months, sometimes more than a year, before the planets realign favorably for the journey back. Mars does not care how tired you are. Earth does not hurry to meet you. So the mission timeline stretches. 6 to 9 months to get there, many months on the surface, and then another 6 to 9 months to come home. Suddenly, the idea of a Mars mission is no longer a journey measured in months, but in years. And that's the thing. When people ask how long it takes to get to Mars, they are often unknowingly asking only half the question. The more honest question is, how long are you gone? How long are you exposed? How long must your body and mind endure an environment utterly unlike the one that shaped them? Life on Mars itself is not a respite. The planet offers gravity, but less than Earth. Enough to remind muscles and bones what weight feels like, but not enough to fully restore them. The atmosphere is thin, offering little protection from radiation. Dust storms can last for weeks, dimming the sky, complicating surface operations. Temperatures swing dramatically. Every activity must be planned, every mistake magnified. And yet, waiting on Mars is unavoidable. Leaving too soon would mean carrying far more fuel to force an early departure, adding mass, cost, and risk. Waiting allows the solar system to do the work for you. It is the same compromise we have seen again and again. Time traded for energy, patience traded for safety. This waiting period becomes one of the most psychologically complex phases of the mission. Astronauts are no longer in transit, moving toward a goal. They are stationary, at least relative to the planet beneath them, but still profoundly distant from home. Earth hangs in the Martian sky as a bright star, no longer a disk, no longer a place you can imagine returning to quickly. Communication delays persist. Rescue is impossible. The crew must maintain systems, conduct science, stay healthy, manage stress, all while knowing that their return date is not flexible. The universe has already decided when they can leave. All they can do is endure until that moment arrives, and when it does, the journey is far from over. The return trip is another long exposure to microgravity and radiation, another test of endurance, another stretch of isolation. By the time astronauts finally re-enter Earth's atmosphere, they may have spent 2 or 3 years away from home. Their bodies will have changed. Their minds will carry experiences few humans have ever known. This is why Mars missions are sometimes described as endurance expeditions rather than voyages. They resemble polar crossings or deep ocean missions more than traditional travel. Once you commit, you are committed fully. There are no shortcuts, no early exits, and perhaps this reframes the question entirely. The challenge of Mars is not speed alone. It is duration, sustaining human life, health, and sanity across years in hostile environments. Speed can help, but it cannot erase the fundamental structure of the mission. Even the fastest plausible outbound journey still leaves you waiting on Mars, still leaves you returning through the same dangers. So when we ask how long a Mars mission takes, the answer is never simple. It is not 6 months. It is not a year. It is an arc of time shaped by orbital mechanics, biology, and patience. An arc that stretches far longer than most people expect. And this realization brings us gently toward the final reckoning. After all the physics, all the technology, all the biological limits and future dreams, what is the honest answer? With what we know now, with what we can realistically do, how long does it really take? Not in aspiration, not in science fiction, but in the quiet language of reality itself. And so, at last, we stand at the edge of the question itself. Not the poetic version, not the dream that drifts so easily through science fiction, but the quiet, stubborn truth that remains when everything else is stripped away. After all the physics, all the engineering, all the biological constraints and cosmic schedules, how long does it really take to go to Mars? The honest answer is not a single number. And perhaps that is the most important thing to accept. With the technology we have today, with chemical propulsion as our backbone and gravity as our guide, the journey from Earth to Mars typically takes between 6 and 9 months. That number is not chosen for convenience. It emerges naturally from the balance of energy, efficiency, and timing that the solar system allows. Push much harder and the costs rise steeply. Go much slower and the risks quietly accumulate. This range is where reality settles. But that number on its own is misleading, because it suggests a finish line where none truly exists. The 6 to 9 months describes only the outbound leg, only the crossing of space between two moving worlds. It does not include the waiting. It does not include the return. It does not include the full weight of the commitment being made. A real Mars mission, planned honestly, stretches far beyond a single transit. 6 to 9 months to get there. Then many months, often more than a year, living on the Martian surface while the planets slowly realign. And then another 6 to 9 months to come home. When you add it all together, the journey becomes something else entirely. 2 years, sometimes closer to 3, a span of time that reshapes bodies, minds, and lives. And that's the thing. Mars is not far in the way we usually mean far. On a cosmic scale, it is next door. Light takes minutes to cross the gap, astronomers call it nearby. But for humans, distance is measured in endurance, not kilometers. And by that measure, Mars is extraordinarily far away. This is why there is no short answer that satisfies both dream and physics. When someone says we could reach Mars in a few months, they are not wrong. When someone else says it would take years, they are also not wrong. They are simply describing different parts of the same story. The universe does not lie to us about this. It lays out the rules clearly. Gravity shapes the path. Energy sets the limits. Biology defines what is tolerable. Radiation keeps count without mercy. And time weaves through all of it, turning every compromise into a lived experience. Perhaps the deeper truth is that the question itself reveals something about us. We ask how long because we are creatures of schedules and lifetimes. We want to know where the end lies, but Mars resists that framing. It demands that we think in arcs instead of points, in seasons instead of moments. And when we do that, the answer becomes less about months and more about meaning. Going to Mars is not a sprint. It is not even a marathon. It is an expedition in the truest sense of the word. Once begun, it cannot be rushed. It cannot be paused. It carries consequences that extend long after the engines fall silent. With what we know now, with what we can reliably build and launch, the realistic answer is this. A human journey to Mars is measured in years, not because we lack ambition, but because the universe insists on it. And until our technology changes in profound ways, that truth will remain. Mars is close enough to tempt us, yet distant enough to humble us. Near in astronomical terms, but far in human ones. And perhaps that balance is not a flaw, but a filter. A reminder that reaching another world is not just about getting there, but about whether we are ready to endure the time it takes, to survive it, and to return changed, carrying a deeper understanding of our place in the vast, patient cosmos. And so even now, after all the numbers have been spoken and all the limits carefully traced, something unresolved still lingers in the air, a quiet echo. Because the journey to Mars, when you look at it closely enough, is not really about Mars at all. It is about us. About how we measure time, how we face uncertainty, and how we respond when the universe refuses to bend to our expectations. We began with a simple question. How long does it take to get to Mars? And at first, it feels like a question that should have a simple answer. A number, a duration. something neat and satisfying. But the deeper we travel into the problem, the more that simplicity dissolves. Time stretches, context appears. The answer fractures into layers, each one revealing something uncomfortable and something beautiful about our place in the cosmos. Because time, you see, is not just a clock ticking on the wall of a spacecraft. Time is the medium through which everything happens. It is the currency the universe charges for movement, for survival, for change. On Earth, we spend time casually. We waste it, we rush it, we complain about it. But beyond Earth, time becomes tangible, heavy, consequential. Every extra day in space leaves a mark, on the body, on the mind, on the mission itself. And that reality forces a kind of honesty that modern life rarely demands. You cannot multitask your way to Mars. You cannot optimize it away completely. You must live inside the duration, and that's the thing. Mars does not allow shortcuts without consequence. Every attempt to hurry the journey demands payment elsewhere. More fuel, more risk, more stress on the human system. The universe keeps its books balanced with ruthless consistency. So when we say that a journey to Mars takes years, what we are really saying is that it takes commitment. It takes acceptance. It takes a willingness to step outside the rhythms that define everyday human life and enter a slower, older rhythm that belongs to the solar system itself. Think about what that means. A crew leaves Earth knowing that there is no turning back, no rescue, no quick return. They know that for years, their lives will be shaped by forces beyond immediate control: planetary motion, radiation, distance measured not in kilometers, but in minutes of communication delay. That is not travel as we understand it. That is exile, willingly chosen. And yet, people still want to go. That alone should make us pause, because curiosity is a strange force. It pushes us beyond comfort, beyond safety, beyond certainty. It has done so throughout history, across oceans, over mountains, into the depths of the sea, and now outward into space. But Mars is different. Mars does not test bravery in a moment. It tests endurance over time. This is why the question of how long it takes matters so deeply. Not because of impatience, but because duration is the true challenge. Speed is seductive, but time is transformative. Time is what changes bodies. Time is what reshapes priorities. Time is what reveals whether systems fail slowly or hold together. Perhaps that is why Mars has resisted us for so long. Not because it is unreachable, but because it asks a more difficult question than technology alone can answer. It asks whether we are capable of sustaining intention across years without immediate reward. In a world trained to expect instant results, Mars asks for something ancient: patience, discipline, trust in preparation rather than improvisation, faith that the work done today will still matter years from now. And when you look at it that way, the long journey stops being a flaw. It becomes a filter. Only a civilization willing to think long-term can seriously attempt it. Only a society capable of caring for human life across vast spans of time can justify it. Mars does not reward impulse. It rewards maturity. And maybe that is why the journey feels perpetually just out of reach. Not because we lack rockets, but because the endeavor itself demands a level of collective patience we are still learning how to cultivate. The universe, in this sense, is not hostile. It is instructive. It does not shout. It does not forbid. It simply lays out the conditions and waits. If you wish to come, it seems to say, then come on my terms. Those terms are written in orbital mechanics, in radiation exposure curves, in biological decay rates, in psychological endurance. They are not negotiable, but they are understandable. And understanding them is already a kind of victory, because every step toward Mars teaches us something about how to live elsewhere, and also, quietly, about how to live here. Life support systems remind us how fragile ecosystems are. Closed loops teach us about sustainability. Delayed communication teaches us responsibility. Isolation teaches us cooperation or exposes its absence. A Mars mission magnifies human behavior the way a vacuum chamber magnifies pressure. Nothing is hidden. Everything matters. And perhaps that is the greatest value of the journey, regardless of whether it happens tomorrow or decades from now. Preparing to go to Mars forces us to confront truths we often avoid, that we are dependent on systems we barely notice, that our bodies are not designed for every environment, that progress is not always acceleration. Mars invites us to slow down enough to see these truths clearly. So when people ask how long it takes to get there, the most honest answer might be this: It takes as long as it takes for a civilization to grow into the responsibility of leaving its homeworld without destroying the lives it carries with it. That is not a number you can put on a launch schedule, and yet the desire remains. The red planet still rises in our night sky, faint but persistent, a reminder that we are not confined by our origins, even if we are shaped by them. A reminder that curiosity does not fade simply because the journey is hard. Mars is close enough to matter, far enough to demand humility, and somewhere in that tension between ambition and restraint lies the future of human exploration, not as a race, not as a conquest, but as a careful extension of life into environments that do not naturally welcome it. Perhaps one day, humans will stand on Mars and look back at Earth as a distant star, and perhaps in that moment, the true meaning of the journey will finally become clear. That reaching another planet was never just about expanding our presence in space. It was about learning how to carry ourselves intact across time. And that lesson, once learned, does not end at Mars. It continues outward, quietly, patiently, into the vast, listening universe beyond. And so the story continues, not forward in distance, but deeper in time. Because once we accept that the journey to Mars is measured in years rather than months, once we accept that it reshapes those who attempt it, another question begins to surface, quietly at first. What happens after that? Not after landing, not after returning, but after the idea of Mars itself settles into human culture as something real, something lived, something no longer hypothetical. You see, the first journey to Mars will not end when the astronauts come home. It will echo. It will change how we think about exploration, about risk, about time itself. It will become a reference point, a before and after, much like the first voyages across Earth's oceans or the first steps on the Moon. But unlike those moments, Mars will not be a brief chapter. It will be a long sentence, written slowly, with consequences that unfold over generations. Because the moment humans commit to Mars, even tentatively, they commit to something much larger than a mission. They commit to continuity. You cannot visit Mars casually. You either go once and stop, or you begin something that must be sustained. Infrastructure, knowledge, experience. The first crew will rely on the next, and the next on the one after that. Time stretches again, this time not just across space, but across human history. And that's the thing. Mars forces us to think generationally, not just about hardware that lasts years, but about institutions, cultures, and values that must persist far longer than any single mission. A Mars program cannot be sprinted. It must be walked, patiently, with care. Perhaps this is why the question of time keeps returning. Time is not merely a constraint. It is the medium in which all responsibility exists. Short projects can tolerate recklessness. Long ones cannot. And Mars, by its very nature, demands long thinking. Imagine what it means to design systems that must work for years without resupply. Life support that cannot fail quietly. Habitats that must protect against radiation day after day. Psychological support that must function even when Earth feels impossibly distant. These are not engineering problems alone. They are ethical ones. How much risk is acceptable? How much uncertainty can be placed on human shoulders? How do you weigh the value of exploration against the cost to those who undertake it? These questions cannot be answered by equations alone. They require judgment, humility, and restraint. And perhaps that is the deeper role Mars plays in our story. It slows us down enough to ask better questions, because speed in human culture often disguises a lack of reflection. We move quickly so we do not have to think too hard about consequences. Mars removes that luxury. Every decision echoes across years. Every shortcut taken early can become a crisis later. The long timeline exposes weaknesses mercilessly. This is why preparation for Mars has already changed how we think about spaceflight closer to home. Closed-loop life support systems, developed for Mars, teach us how to recycle air and water more efficiently on Earth. Radiation studies deepen our understanding of cancer and cellular repair. Research into isolation informs mental health work in remote environments here on our own planet. Mars, in this way, becomes a teacher long before it becomes a destination. And yet, for all this seriousness, the human element remains stubbornly emotional. People still look up at the night sky and feel wonder. Children still imagine standing on another world. That spark has not dimmed. If anything, understanding how hard the journey really is makes that spark burn more brightly. Because wonder that survives realism is stronger than wonder built on illusion. When we imagine future generations reading about the first Mars missions, it is unlikely they will focus on the exact travel time. They will not argue whether it was 6 months or 8. They will remember the commitment, the courage, the willingness to accept years of uncertainty in pursuit of knowledge, and perhaps they will also remember the restraint, the decisions not taken, the moments when humanity chose not to rush, not to gamble lives for headlines. Those choices, quiet and invisible, may matter just as much as the dramatic ones. Exploration is often framed as expansion, but Mars suggests another framing. Exploration as refinement, as learning how to carry life carefully into places where it does not naturally belong, as learning how to respect environments rather than dominate them. Time plays a central role in that lesson. Rushed systems break. Rushed societies fracture. Rushed exploration leaves scars. Mars gives us no choice but to move deliberately. And perhaps that is why the question of how long it takes to get there never truly resolves. Because the journey is not just between planets, it is between versions of ourselves, between a species that reacts and one that anticipates, between short-term thinking and long-term stewardship. If we ever become a multi-planetary species, it will not be because we built faster engines alone. It will be because we learned how to think in decades and centuries without losing compassion for individual lives. Mars is a test of that capacity, and the test is ongoing. Even now, as plans are drawn and redrawn, as technologies inch forward, as debates continue, the red planet remains where it has always been, circling the sun, waiting, not impatient, not impressed, simply there. It does not demand that we come. It does not promise that we should. It merely exists, offering the same silent invitation it has for billions of years. If you wish to know me, it seems to say you must accept my timescale. And that invitation, once understood, changes its meaning. It is no longer a challenge to be beaten. It is a conversation to be entered. So the journey continues, not necessarily with a launch, but with a mindset, with the slow alignment of technology, ethics, and patience, with the recognition that some destinations are valuable precisely because they cannot be reached quickly. And as we carry that understanding forward, beyond Mars and toward whatever comes next, one truth remains clear. The most important journeys humanity undertakes are rarely the fastest ones. They are the ones that teach us how to live with time rather than against it. And so, almost without noticing it, our attention drifts even farther outward, beyond Mars as a destination, beyond missions and timelines and even generations. Because once we accept that Mars is not a journey to be rushed, another realization settles in, slowly and gently. Mars is not the end of the road. It is the beginning of a different relationship with the universe. You see, for most of human history, space has been something we looked at. We measured it. We mapped it. We wondered about it. Even when we sent machines into it, space was still something external, something separate from the flow of human life. Mars changes that. The moment humans commit to living, even briefly, on another planet, space stops being an abstract backdrop and becomes part of our lived environment. And that changes everything. Time, once again, is the key, because living beyond Earth means synchronizing human life with non-human rhythms. Martian days are longer than Earth days. Martian years are almost twice as long. Seasons stretch differently. Dust storms obey no familiar calendar. Light arrives softer, colder. Night falls with a different weight. Humans arriving on Mars will have to decide which clock they live by. Earth time or Mars time. Biological time or orbital time. And these choices, subtle as they seem, will ripple outward into culture, psychology, even identity. What does it mean to wake up to a sunrise that lasts longer than you are used to? To celebrate a year that takes almost 2 Earth years to complete? To measure age in sol cycles instead of birthdays? These are not technical problems. They are existential ones. And perhaps this is where Mars begins to shape us more than we shape it. Because adaptation is never one-sided. Environments change organisms as much as organisms change environments. Over long enough timescales, habits become instincts. Routines become traditions. A generation born knowing only Earth sees the universe one way. A generation that knows Mars, even indirectly, sees it another. And that brings us back once more to time. The long view. If humans ever establish a sustained presence on Mars, even a small one, it will mark the first time life from Earth has intentionally carried itself across interplanetary time. Not just across distance, but across cycles of planetary motion, radiation exposure, evolutionary pressure. That is not exploration in the traditional sense, it is dispersal. And dispersal carries responsibility. We often imagine spreading into space as expansion, but biology teaches us something quieter. Dispersal only succeeds when life adapts carefully, conserves resources, and respects limits. Species that expand recklessly collapse just as quickly. Mars does not forgive excess. It does not replenish easily. It does not recover quickly from mistakes. So again, Mars asks for restraint. It asks us to think not just about getting there, but about staying alive without exhausting what little protection and stability we bring with us. It asks us to build systems that recycle perfectly, that waste almost nothing, that fail loudly rather than silently. These are the same challenges Earth now faces, compressed into a harsher environment. In this way, Mars becomes a proving ground, not for dominance, but for stewardship. Can we maintain life without exploiting an ecosystem that cannot replenish itself? Can we plan for decades without knowing who will inherit the outcome? Can we design missions whose success depends on care rather than speed? And this loops us back to the original question in a way that feels almost poetic. How long does it take to get to Mars? Long enough that the question forces us to slow down and think about what we are doing and why. Because if Mars were easy, we might treat it carelessly. If it were close, we might arrive unprepared. Its distance is a kind of protection, not just for us, but for the idea of exploration itself. Perhaps that is why the universe seems structured the way it is. Vast distances, slow orbits, harsh environments, not as barriers but as filters. They ensure that only intentions strong enough, thoughtful enough, make it through. And this idea extends beyond Mars. Once we begin thinking this way, the rest of the solar system comes into view differently. The moons of Jupiter, the icy worlds beyond Saturn. Each one is not just farther away, but slower to reach, slower to leave. Each one demands deeper commitment. Mars, then, is a threshold, a test case for whether humanity can operate on cosmic timescales without losing its ethical compass. And ethics, you see, are inseparable from time. Short-term thinking allows harm to be hidden. Long-term thinking exposes it. Mars missions unfold too slowly to hide mistakes easily. The consequences of decisions made today will be experienced by people years later, far from the decision makers themselves. That forces a kind of moral maturity. Who decides who goes? Who decides what risks are acceptable? Who bears responsibility if something goes wrong when rescue is impossible? These questions do not have clean answers, but Mars insists that they be asked honestly. And maybe this is the greatest contribution Mars will make to humanity, regardless of how many footprints eventually mark its surface. It forces us to confront the reality that technology alone does not define progress. Wisdom does. Wisdom to wait when waiting is safer. Wisdom to stop when stopping is wiser than pressing on. Wisdom to accept that some achievements matter precisely because they are difficult and slow. In that sense, Mars is not calling us to hurry toward it. It is asking us to grow into the kind of civilization that deserves to arrive. And as we look beyond Mars, beyond even the solar system, this lesson becomes more important, not less. The universe is vast beyond comprehension. Our lifetimes are brief. Our technologies change rapidly. Only our capacity for long-term thinking can bridge that gap. So the journey continues not with a countdown, but with a cultivation of patience. With the quiet work of building systems that can endure, cultures that can sustain meaning across distance, and individuals willing to live with uncertainty for years at a time. And somewhere far ahead in that unfolding future, Mars remains what it has always been. Not a finish line, but a conversation. One that unfolds slowly over generations, carried forward by those willing to listen to time rather than race against it. And that conversation, once begun, does not end at Mars. It carries us onward, gently, into whatever chapters come next. And so the horizon widens once again, almost imperceptibly at first, because after Mars becomes imaginable as a place we might reach, endure, and perhaps even return from changed, another idea begins to take shape. Not a destination, but a continuity. A sense that the act of going outward is not a series of isolated missions, but a long unfolding process in which humanity slowly learns how to exist beyond the narrow cradle of its birth. What Mars teaches us, perhaps more than any other world, is that space is not an arena for quick victories. It is a medium that stretches intention across time. And once that lesson settles in, we begin to see our technologies, our institutions, and even our stories differently. Think about how rarely on Earth we design anything to last decades without constant intervention. Cities change, systems are replaced, software becomes obsolete almost as soon as it is deployed. But a Mars mission does not allow that rhythm. It forces us to build things that must endure quietly without applause, without constant repair crews, without replacement parts arriving overnight. That endurance is not glamorous. It is not dramatic. It is careful, almost humble. And yet, it may be the most profound shift Mars demands of us, because enduring systems reflect enduring values. To sustain life far from Earth, we must value reliability over novelty, foresight over speed, cooperation over competition. A spacecraft bound for Mars cannot afford ideological battles or fragmented authority. It must function as a coherent whole, or it fails. And that coherence is not just technical. It is social. A crew living together for years, isolated from Earth, exposed to constant risk, cannot rely on hierarchy alone. They must rely on trust, on shared purpose, on the quiet competence of individuals who understand that their own survival is inseparable from the survival of everyone else. Mars, in this sense, is a crucible. It strips away illusions about independence. It reveals how deeply interconnected we truly are. One mistake in maintenance, one overlooked procedure, one ignored warning. The consequences ripple outward, touching every life aboard. And that awareness, once experienced, does not vanish when the mission ends. It reshapes how people think about systems back home, about supply chains, about environmental balance, about the invisible work that keeps complex structures alive. Perhaps that is why Mars feels so relevant to this moment in human history. We are, collectively, beginning to realize that Earth itself is a closed system. Finite resources, delayed feedback, long-term consequences that cannot be easily reversed. In a strange way, Earth is becoming more like a spacecraft every year. Mars simply makes that reality impossible to ignore. When you imagine future generations studying the first Mars missions, they may not focus on propulsion or travel time as much as we do. They may study how decisions were made, how risks were communicated, how crews were selected and supported, how failures were anticipated rather than denied. They may ask whether we treated those first travelers as heroes or as expendable symbols, whether we valued their lives as much as the idea of going itself. These questions linger long after engines cool and headlines fade. And this brings us back yet again to time. Because ethical clarity often requires time, the ability to pause, to reflect, to resist the pressure of spectacle. Mars does not reward haste, it rewards care. The universe, in its vast indifference, becomes a kind of moral amplifier. It does not judge our intentions, but it exposes their consequences with unforgiving precision. In space, errors are not hidden by distance or delay. They unfold slowly, visibly, often tragically. So perhaps the long journey to Mars is not a flaw to be solved, but a feature to be respected. It forces deliberation. It creates space for doubt. It gives weight to choice. And when you consider that, the question of how long it takes to get there begins to feel almost secondary. The more important question becomes how long we are willing to prepare before we go. How long we are willing to listen to what the universe has already taught us through physics, through biology, through history. Because the universe is not silent. It speaks through constraint, through limit, through consequence. And Mars is one of its clearest messages. It says you may come, but only if you accept that you are not in control of everything. Only if you accept that survival depends on harmony with forces older and larger than yourself. Only if you accept that progress is measured not just in distance traveled, but in wisdom gained. And perhaps that is why the journey continues to unfold chapter by chapter, rather than arriving at a single, definitive conclusion. Each generation adds a layer of understanding. Each mission refines the question. Each delay teaches patience. Mars is not waiting for us in the way a finish line waits. It is simply there, moving along its ancient path, indifferent to our schedules. And in that indifference lies its power as a teacher. As we carry this understanding forward, we begin to sense that Mars is not the ultimate goal. It is a threshold, a test of whether humanity can step beyond Earth without abandoning the principles that allow life to flourish. And once that threshold is crossed, even tentatively, the universe beyond begins to look different, not as an expanse to be conquered, but as a continuum to be entered carefully, one patient step at a time. So the story goes on. not toward an ending, but toward deeper questions about how we sustain meaning across distance, how we pass knowledge across generations, how we remain human in environments that do not care whether we survive or not. And somewhere ahead, beyond Mars, beyond even the solar system, those questions will arise again, reshaped by new distances and new durations. And when they do, the lessons learned on the long, slow road to Mars will still be speaking quietly, guiding whatever journey comes next.